In this video tutorial, we're going to be analysing a steam power plant operating on the Carnot cycle. So on the screen in the top right hand corner, first of all, we have our schematic diagram of the plant equipment that's included in the Carnot cycle, and we also have a temperature entropy diagram to represent this cycle. Underneath the diagrams we have a descriptive question, so we're going to work through the descriptive question, we're going to extract the relevant information, and we're also going to use our temperature entropy diagram in order to determine various different pieces of information about the condition of the steam at different points throughout this cycle. So to begin with then, we're told that the steam power plant operates on the Carnot cycle, where the boiler pressure is 20 bar and the condenser pressure is 0.5 bar. Now, we know from the previous tutorial that we assume that the operations in both the boiler and condenser are constant pressure. So in the boiler we have constant pressure heating, and in the condenser we have constant pressure cooling or constant pressure condensation. So the very first statements we can write then are P2 equals P3, and we know our boiler pressure is 20 bar. Now repeating that for the condenser then, we know that P4 equals P1, and they both equal 0.5 bar. So what we're saying here is that the pressure at the entrance and exit to the boiler are equal, and the pressures at the entry and exit of the condenser are also equal. We have constant pressure heating and constant pressure cooling. We're told something else about the steam. The steam exiting the boiler is dry saturated. Now if we refer to our temperature entropy diagram at the exit to the boiler, or position 3, then we know that we have dry saturated steam there because it sits on the dry saturated vapour line. Anytime we're on this side of the curve we have dry saturated vapour, and anytime we're on this side of the curve we have wet saturated vapour or saturated water. So we're told that the steam exiting the boiler is dry saturated and then it's expanded in an isentropic process until the condenser pressure of 0.5 bar is reached. Well, this supports what we said before because we know our condenser operates at 0.5 bar. We've said that P4 equals 0.5 bar. So at position 4 on our temperature entropy diagram, we know that we have wet steam at a pressure of 0.5 bar. The other thing it tells us there is that we have an isentropic process, and once again we can see that from our temperature entropy diagram, because if we have an index mark here on our entropy axis, we can see that at position 4 and position 3 we have the same entropy. The reason we know we have wet steam here is because anything under the curve represents wet vapour. Anything to the right represents superheated steam, anything to the left represents water, and anything under the curve is wet steam or wet vapour. We're going to need to determine the dryness fraction of our steam at position 4 later on, but what we can write for the time being is S3 equals S4. Next we're told that the steam exiting the turbine is partially condensed. The reason it's only partially condensed is because moving from position 4 to position 1, we're not reaching the wet saturated vapour line here. So there's still going to be moisture in that steam, hence it's only being partially condensed. Next it tells us that after exiting the condenser, it's compressed until it changes back to saturated water prior to entering the boiler. Well, going from position 1 to position 2 through the compressor, we know that the exit of the compressor is saturated water or wet saturated vapour. Now once again 1 to 2 we can see is an isentropic process, constant entropy. So the entropy at position 1 equals the entropy at position 2, and once again we'll be determining those values later in this video. The last piece of information then that we're given is the mass flow rate of the steam throughout the cycle is 0.85 kilograms per second. So all of the information that we've extracted from the descriptive question and the diagram there is written in the top left hand corner in blue. So what are we actually asked to do then? Well, down here at the bottom we're asked to determine the enthalpy of the steam throughout the cycle. So we know that we need to determine H1, H2, H3 and H4, and we're going to be using our steam tables to determine each of those values. We're then asked to determine the energy transfer at each stage and the thermal efficiency of the steam plant. So we're going to clear the screen and we're going to work round our cycle and determine our enthalpy values at each of those positions, H1 to H4. Okay, so the first two enthalpy values that we're going to find are H2 here and H3 here. The reason we're going to start here is because we know that the enthalpy at position 2 is the enthalpy of wet saturated vapour, so HF, at our higher pressure of 20 bar. Now the reason we know that is because from positions 2 to positions 3 we have our boiler, and we know that our boiler operates on our higher pressure of 20 bar. Now we also know at position 3 that we have dry saturated vapour, Hg, also at 20 bar. So we go from wet saturated vapour to dry saturated vapour in our boiler, and that process occurs at 20 bar. So let's go to our steam tables, and we're looking for HF and Hg at 20 bar. HF is our H2 value and Hg is our H3 value. So here we have the first page of the steam tables that you've been provided with, and we notice that the first table is for saturated steam, and we notice that we have F and G values for saturated liquid and saturated vapour. The reason we're not going to use this first table here is because the reference column, or the left-hand column over here, uses temperature as the reference. Now we've been given pressures, so if we scroll past our first page, our second page also references temperatures, but if we scroll to our third page, we notice that the reference is pressures. Now we've said that our boiler pressure is 20 bar. We have various information at 20 bar. We have a temperature, we have specific volume values, we have internal energy values, and then we have enthalpy of saturated liquid, enthalpy of saturated vapour, entropy of saturated liquid, and entropy of saturated vapour. Now recall that we're looking for HF at 20 bar and we're looking for Hg at 20 bar. So HF at 20 bar is 908.8 and Hg at 20 bar is 2800. Let's return and make a note of those values. HF at 20 bar we said was 908.8. The units there are kilojoules per kilogram. And Hg was 2800 kilojoules per kilogram. If you're unsure of the units there, then you can check on the steam tables in the top of the column for enthalpies. Now, before we find H1 and H4, we need to do a little bit of extra work. And the reason being is because we know at position 1 and 4 we have wet vapour, but we don't know the dryness fraction of that vapour. What we do know though is that at position 3 and position 4 the entropy is equal. And we also know that at position 1 and position 2 the entropy is equal. The entropy at position 3, for the same reasons discussed for the enthalpy, is going to equal Sg at 20 bar. The reason being there is we know that at position 3 we have dry saturated vapour. Now we also know that at position 2, here we have wet saturated vapour. We know that the pressure is 20 bar because that's the entrance to our boiler. So we can determine our entropy values at position 3 and position 2, and then we can set them equal to positions 4 and 1. So returning to our steam tables at 20 bar, we've extracted our enthalpy values, but we also need the entropy values that correspond with our steam at 20 bar for both wet and dry saturated vapour. So I've previously highlighted these values because at 20 bar we know that SF is 2.447 and Sg is 6.341. Let's take those values back across and then we can work out the dryness fraction of our steam at position 4 and position 1. So Sg at 20 bar is 6.341 This time our units are kilojoules per kilogram Kelvin. And SF at 20 bar was 2.447. With the same units, kilojoules per kilogram Kelvin. Okay, so what we've determined there is that the entropy at position 3 is 6.341. But we know that the entropy at position 4 is also 6.341 because S3 equals S4. So let's make a note of what we know about position 4 then. First of all, we know S4 equals 6.341 kilojoules per kilogram Kelvin. But we also know the pressure at position 4 because the pressure at position 4 is our lower pressure, or our condenser pressure, of 0.5 bar. We know at position 4, our enthalpy sits somewhere between the dry saturated vapour enthalpy and the wet saturated vapour enthalpy. And we also know that the dryness fraction sits somewhere between a dryness fraction of 0 and a dryness fraction of 1. What we don't know is what that fraction is at the moment. We do know our entropy. We do know our pressure. So what we can do using our steam tables is look up the entropy of wet saturated vapour or saturated water at 0.5 bar. We can also look up the entropy of dry saturated vapour at 0.5 bar. And our entropy value of 6.341 is going to sit between those two values. We can then use a process of linear interpolation to determine where we sit on that continuum, and hence we can work out our dryness fraction. So, SF and SG at 0.5 bar, we can look those up in our steam tables. This time then, we're referring to 0.5 bar, or our condenser pressure. Once again, I'm going to highlight our enthalpy values because they're going to be used later. And I'm also going to highlight our entropy values. We have an SF value of 1.091 and an SG value of 7.594. Let's transfer those across and determine our dryness fraction. Okay, so we have an SF value of 1.091 kilojoules per kilogram Kelvin, and we have an SG value of 7.594 kilojoules per kilogram Kelvin. So we have a couple of formulas that link our entropies and our enthalpies to the values for the wet saturated vapour and the dry saturated vapour. The first then is entropy equals SF plus X SG minus SF. This is a form of linear interpolation. And we have the same formula for our enthalpies. H equals HF plus X HG minus HF. If we rearrange this formula to make dryness fraction the subject, then we can subtract SF from each side, and then we can divide each side by SG minus SF. So we're going to get dryness fraction X equals S minus SF divided by SG minus SF. Now we know that this value is going to sit somewhere between 0 and 1, and we know it's going to be closer to 1. The reason we know it's closer to 1 is if we refer to our temperature entropy diagram, we can see that position 4 is closer to the dry saturated vapour line than it is the wet saturated vapour line. I'm just going to put a subscript 4 down here just to remind us that it's position 4 we're working on here, and the same for our X, because in a moment we're going to need to repeat this for position 1. But we have S4 6.341 minus SF 1.091 over SG 7.594 minus SF 1.091. Now that gives us a dryness fraction for the steam at position 4 equal to 0.80732, accurate to 5 decimal places. Now I'm going to make a note of that dryness fraction on the left hand side because we need to repeat the calculation in order to determine x1. So we have x4 equals 0.80732. Let's make a note, x1 equals, we're going to determine that next. Okay, I'm going to remove the information we no longer need, but I'm going to keep our values of SF at 0.5 bar and SG at 0.5 bar. But this time, because we're repeating for position 1, we can lose the information about position 4. And I'm also going to keep our two formulas that connect our enthalpies and entropies to our dryness fraction. However, this time we're working on position 1. Now we know that at position 2, S2, our entropy is 2.447. But we also know, because the compression is isentropic, S1 equals S2, which equals 2.447. We're interested in position 1, so we have S1 equals 2.447 kilojoules per kilogram Kelvin. We also know the pressure at position 1 because the pressures at position 1 and position 4 are our condenser pressures of 0.5 bar. So this time we don't need to look up our values of SF and SG because we've already looked those up. The condenser operates at 0.5 bar, so when we come to calculating our dryness fractions, we still use our value of SF at 0.5 bar and our value of SG at 0.5 bar. So we're picking up with our calculation of X. Recall we rearranged this formula to make X the subject, and we said that X equals S minus SF over SG minus SF. The difference this time is we're using the entropy at position 1 because we want the dryness fraction at position 1. Our entropy at position 1 is 2.447. So we have 2.447 minus 1.091 over 7.594 minus 1.091. Remember to include your brackets. Giving us a dryness fraction at position 1 this time equal to 0.20852. Now once again, I'm going to make a note of that on our left hand side. So we have 0.20852. The equation that we're going to use to find our enthalpies is this equation here. I'm going to rewrite it so that we can work through these calculations, but the enthalpy at position 4 will be the enthalpy of the wet saturated vapour plus the dryness fraction multiplied by the difference between the enthalpy of the dry saturated vapour and the wet saturated vapour. Okay, so because we're trying to find our enthalpy at position 1 and our enthalpy at position 4, we know that our reference pressure, P1, which is equal to P4, equals 0.5 bar. That's our condenser pressure. So this time we need to find HF at 0.5 bar, and we need to find HG at 0.5 bar. Now fortunately, when we return to our steam tables, we've already highlighted those two values. So here we are at 0.5 bar. HF at 0.5 bar is 340.5 and HG at 0.5 bar is 2646. So let's take those values across and finish our calculations. HF 340.5 kilojoules per kilogram and HG 2646 kilojoules per kilogram. Now this time we don't need to rearrange our equation because we're actually trying to find the enthalpy at each of those positions. So if we refer to the top, we can write H1 equals HF plus X1 times HG minus HF. H1 then equals HF 340.5 plus the dryness fraction at position 1, 0.20852, and then we're multiplying that by Hg 2646, and then we're subtracting HF 340.5, giving us an enthalpy at position 1 equal to 821.24 kilojoules per kilogram. Let's make a note of that on our left-hand side. We have H1 equals 821.24 kilojoules per kilogram. So we can do exactly the same for position 4. The only difference at position 4 is that we need to use the dryness fraction at position 4. So if we refer to our formula right at the top there, we're looking for the enthalpy at position 4 instead of position 1. So we need to use the dryness fraction at position 4 instead of position 1. So we can write H4 equals HF again, 340.5, plus our dryness fraction this time is 0.80732. Hg remains the same, 2646, and HF remains the same, 340.5. This time giving us an enthalpy at position 4 equal to 2201.78 kilojoules per kilogram. So making a note, 2201.78 kilojoules per kilogram. So we've had to do quite a lot of work there to determine our enthalpy values at each of our locations. But now we have that information, we have some relatively straightforward calculations to do to determine the energy transfer at each stage and hence the efficiency of this steam cycle. Okay, so the energy transfer during each stage is the mass flow rate times the change in enthalpy. So if we start with our compressor then, our compressor does work on the steam. As we're doing work on the steam, we write that as P in, mass flow rate, and the change in enthalpy. At the exit we have the enthalpy H2, and at the entrance we have the enthalpy H1. So P in then is our mass flow rate, given in the question as 0.85. H2 we have given as 908.8, and H1 we have 821.24, giving us a power input equal to 74.43 kilowatts. The reason we have kilowatts there is because our enthalpy values are in kilojoules per kilogram. So after we've compressed the steam, the next thing we do is we heat it in the boiler. So we can write Phi in equals the mass flow rate again, m dot, and the enthalpy values either side of the boiler. We have H3 at the exit minus H2 at the entrance. Therefore we have 0.85, H3 is 2800, and H2 is 908.8. Giving us a Phi in value equal to 1607.52 kilowatts again. So once we've heated the steam, we expand it in the turbine. And when we expand the steam in the turbine, the steam is doing work on the system or on the turbine to produce power output. So this time we have P out equals m dot. The enthalpy at the exit of the turbine is H4, and at the entrance we have H3. So we have 0.85. H4 is 2201.78. And from that we're subtracting H3, which we already said was 2800, giving us a power output then equal to minus 508.49. Okay, just a point to note here, The reason that's negative is energy is being transferred away from the working fluid or the steam. So the steam is losing 508.5 kilowatts, but that's being converted into mechanical work. So we're actually producing 508.5 kilowatts of work when we expand this steam. And we'll see why this is important in a moment. So to a certain extent you can ignore that negative sign, but what it's telling us is that as a thermodynamic process, the working fluid is losing energy. Our final process then is the heat out, which occurs at the condenser. Now once again this is going to be negative because heat energy is leaving the working fluid, but we can prove this. We have the mass flow rate. At the exit of the condenser we have position 1, so H1, and at the entry we have position 4. So this time we have 0.85, position 1, 821.24, minus position 4, 2201.78, giving us a thigh out value then equal to minus 1173.46. Okay, let's clear a little space in the top left hand corner there, and then we'll carry out our very final calculation. So our final calculation then is for the efficiency of this cycle. And the efficiency of the cycle is the net power output. Well, by the net power output, we mean the power that we get out of the system minus the power we put in. So in effect, it's the amount of useful work that results. And that's divided by the amount of heat energy that we put into the system. Well, we have all of these values now. We have a P out value, and we're going to use the absolute value, or the magnitude, 508.49. And the reason for that is because we're trying to determine how much useful energy we're producing. The amount of power that we were inputting then was 74.43. And we're dividing that by the heat input, which was 1607.52. Just before we finish that calculation, it is worth noting that 508.49 minus 74.43 gives us a net power output of 434.06. So the top of the fraction here for the net power output is 434.06. So that's the resulting net power output that we're actually extracting from this process once we deduct the amount of power that we're inputting. But carrying that through and dividing by the rate of heat that we're inputting into this cycle, we get an overall thermal efficiency equal to 27.0%. Now interestingly, we can check that value for a Carnot cycle because we actually have another formula that can be used to work out Carnot efficiency. Now, this only applies for a Carnot cycle, but what we also know is that the Carnot efficiency is 1 minus the low cycle temperature divided by the high cycle temperature. Note that each of those temperatures need to be in Kelvin. So we know that our low cycle temperature occurs in the condenser, and we know that the pressure that corresponds with the low cycle temperature is 0.5 bar because that's our condenser pressure. And we know that the pressure that corresponds with our high cycle temperature in the boiler is 20 bar. So just for completeness, we can use our steam tables to determine our low cycle temperature and our high cycle temperature, because those are the temperatures that correspond with the change of state at 0.5 bar and 20 bar. So already highlighted, we have 0.5 bar as a pressure, and the temperature that the change of state occurs at there is 81.33 degrees C. We're going to need to convert that to Kelvin, which we'll do in a moment. At 20 bar, the temperature that corresponds with 20 bar, where the fluids change in state from wet vapour to dry vapour, of 212.4 degrees C. Now once again, we're going to convert each of those values and check our efficiency calculation. So our low temperature then is 81.33. We need to add 273.15 to get that in Kelvin, giving us a low cycle temperature equal to 354.48 Kelvin. And our high cycle temperature corresponded with 212.4 degrees C, but once again adding on 273.15, giving us a high cycle temperature equal to 485.55. Therefore, our Carnot efficiency is 1 minus 354.48 divided by 485.55, giving us an efficiency equal to, and no surprises there, we get a value of 27.0%. So just to summarise, in this video tutorial, we were asked to determine the energy transfer at each stage during our Carnot cycle. But before we was able to do that, we needed to determine the enthalpy at position 1, 2, 3 and 4. Finding some of those enthalpies was relatively straightforward, but in other instances we had to determine the dryness fraction before we was able to determine the enthalpy. And finally, we was able to calculate our Carnot efficiency by determining the net power output divided by the rate of heat input. We carried out a final check of our Carnot efficiency using an alternative formula where the Carnot efficiency is 1 minus the cold cycle temperature over the hot cycle temperature, where each of those temperatures must be expressed in Kelvin.